So, hello and greetings. This is Dr. VC Sontake. The objective of today's this video lecture is to derive and explain governing differential equation for one-dimensional steady-state heat conduction. Sorry, it is heat. It is not hot. Heat conduction through extended surfaces, and they are also called as fins. So, I am going to discuss one-dimensional steady-state heat transfer along a rod. This rod can be served the purpose of fin, and its shape and size can be anything. So, this derivation is also called as derivation of governing differential equation for heat transfer through fins. So let us consider one such application of extended surfaces. As you can see in figure A and figure B, straight rectangular fin in the form of rectangular fin and fin with circular profile are attached to the base surface. So consider a straight fin of rectangular and circular profile protruding from a wall surface as shown in figure. Let this ball, also called as base surface, be at surface temperature Ts, which is higher than the surrounding air temperature at T infinity to which it is exposed. The wall temperature along the length goes on decreasing. The fin in both the cases has a uniform cross-sectional area AC, perimeter P, length L and thickness delta if it is of rectangular cross-section. So as you can see here, for this rectangular cross-sectional fin, its width is B, length from the base surface is capital L, its cross-sectional area is represented by AC and perimeter is represented by capital P. And if this fin is of circular profile, its diameter is small d and its length from the base is capital L. The heat transfer coefficient between the surface of the fin and the surrounding fluid to which the base surface and fin are exposed is small h, watt per meter square Kelvin. Okay. Now what happens? This base surface is at temperature Ts, and when the fin is attached to this base surface, whether a straight rectangular fin or circular profile fin, the temperature of the base, the temperature of the fin at the base, it is also called as root of the fin. So this area particularly, this is also called as root of the fin, and this portion is called as tip of the fin. So temperature of the fin at the root will be equal to temperature of the base surface, that is Ts, and this temperature of the fin goes on decreasing as we move away in the x direction. and the temperature of the fin will be minimum at the tip of the fin here. Okay. So if I am considering cross-sectional area and perimeter of both the fins, for straight rectangular fin, cross-sectional area will be width into thickness, B into delta, and perimeter P will be twice into B plus delta. And for fin, that is fin of circular profile, cross-sectional area will be pi by 4 d square. This will be the cross-sectional area, and its perimeter capital P will be pi d. Okay, so these are some of the geometrical parameters and temperature and fluid properties parameter shown in the figure A and B. Now, in order to do the analysis of heat conduction through this fin attached to the base surface, we are going to follow some assumptions. Assumption number 1 is thickness of the fin is small compared with its length and width. The fin is very thin as compared to its width and length. So delta can be very less as compared to small b and L. And many cases you will find in subsequent discussion we used to neglect this delta, that is thickness of the fin. Assumption number 2, the temperature at any cross section of the fin is uniform. That is, T is a function of Fx only. In other words, the heat conduction is one dimensional only. What am I assuming? The temperature is varying only along the length of the fin in the x direction. The temperature in other two directions, that is in y and z direction, temperature is constant. It is not going to vary. 3. The fin material is homogeneous and isotropic. Hence, the thermal conductivity of the fin material is uniform. Let's say it is small k. Thermal conductivity is constant with respect to direction. It is kx is equal to ky is equal to kz is equal to k. 4. The heat transfer coefficient of the surrounding fluid to which the base surface and fin is exposed is uniform over the entire fin surface, and it is considered as H watt per meter square Kelvin. 5. There is no heat generation within the fin itself, that is volumetric heat generation Q dot G is equal to 0. 6. Joint between the fin and the heated wall surface offers no contact resistance, and hence temperature at the root or base of the fin is uniform and equal to the temperature Ts of the wall surface. Now what is this assumption number 6 actually? What happens? If I am considering this base surface, okay, and let's say this circular profile fin is attached. So what is happening here? Two surfaces are in contact, base surface and fin surface. So we know here thermal contact resistance may come into picture because the joint between base surface and the fin surface is not going to be perfect. There may be some voids, and these voids will be filled with the air, and because of this joint may offer thermal resistance in the form of thermal contact resistance to the heat conduction. So we are neglecting The effect of any such thermal contact resistance while analyzing one-dimensional steady state heat transfer through a rod. Okay, so this thermal contact resistance will be zero. And what will be the consequence of this assumption? The base surface temperature Ts and temperature of the fin at the root will be same, and that is equal to Ts. Okay, here. Assumption number 7, heat transfer by radiation is negligible. I am considering heat transfer only by conduction and convection. And last but not the least assumption, the heat conduction is in steady state. That is, variation of temperature is taking place only in x direction. However, it is constant with respect to time. So its time derivative dtx by d tau is 0. Temperature is always going to remain constant at a particular distance x from the base surface of the fin. Now, after making these assumptions, what is happening? Heat is being conducted into or along the length of the fin and convected from its surface. So, what is happening? When this fin is attached to the base surface, here, heat is being conducted from base or root of the fin towards the tip along the body of the fin. Also, heat is also convected from the surface of the body as well as surface of the fin. So, there are two modes of heat transfer, conduction as well as convection. Now, in order to analyze or to derive governing differential equation for heat transfer through fins, let us consider an infinitesimal central stripe of thickness dx at a distance x from the base surface. So this is that stripe I have considered at a distance x from the base surface, and its thickness is dx. Okay, thickness of this elemental stripe will be dx, its width will be b, and its thickness will be delta. Now what is happening into this stripe? Heat is entering into this elemental stripe by conduction. Heat is leaving this stripe by conduction, and heat is also convected out of this stripe by convection. Okay. Once again, please understand, if I am considering this elemental stripe, heat is entering by conduction at the rate qx, heat is leaving this stripe by conduction at the rate qx plus dx, and heat is also convected out of this elemental stripe, and this is at the rate of convection is q convected. Okay. So first, the rate of heat conduction into the elemental stripe at a distance x. From the Fourier's law of heat conduction, I can calculate this rate of heat conduction into the elemental stripe qx by the equation minus Ka dTx by dx at the distance x, where Tx is this temperature, the variation of the temperature of this elemental stripe in the x direction. In this Fourier's law of heat conduction equation, A is considered as area normal to the heat transfer. Okay, this will be the area which is normal to heat transfer. And for rectangular film, it will be cross-sectional area, or for circular fin as well, it will be cross-sectional area AC. Isn't it? This is the area which is normal to the heat transfer. So Qx will be minus KAC dTx by dx at the distance of x. This is the rate of heat conduction into the elemental stripe. Let's say this is equation number 1. Similarly, the rate of heat conduction out of the elemental stripe at a distance x plus dx. Now I am talking about this face, right face of this elemental stripe, and heat is leaving by conduction to this elemental stripe at the rate qx plus dx. So once again, from Fourier's law of heat conduction, the equation can be written as q suffix x plus dx is equal to KAC dt suffix x plus t dx. Okay, at this phase, temperature is considered as x plus dx over dx at a distance of x plus dx. Okay. Now, this temperature at the right face of the elemental stripe Tx plus dx can be written as Tx plus dTx by dx into dx. Okay, this temperature Tx plus dx is equal to Tx plus dTx by dx into dx. Now let us put the expression for Tx plus dx into this expression equation. So Qx plus dx will be equal to, here minus sign is also there, minus KAC d by dx into Tx plus dTx by dx into dx at the distance of x plus dx. Let us say this equation is equation number 2. So we have found out the expression for qx plus dx. Now rate of heat convected from the elemental stripe. Heat is also convected from this fringe surface at the rate q convection. So from Newton's law of cooling, Q convected will be H, and what will be the surface area of this elemental stripe from which heat is being convected out of this elemental stripe to the environment? It will be A dx, surface area of this thickness dx, into Ts minus T infinity. Okay. So AdX, that is surface area of heat convection, will be also written as P into dx, where P is perimeter. So Q convection is equal to H into P dx into Ts minus T infinity. This is equation number 3. So now we have mathematical equation for Qx plus dx and Q convection. Now let us take the stock of all these 3 equations and let us apply energy balance into this elemental stride. So when I apply energy balance to this elemental stride, summation of all the heat transfer in the x direction will be 0. So what are the different heat transfer involved? It is heat conduction into the elemental stripe. It is entering into the elemental stripe, so I will be taking it as a positive. Heat leaving the elemental stripe in the x plus dx direction. It is leaving, so I will consider its sign as negative. Similarly, heat is also being convected out of this elemental stripe. It is leaving, so I am considering its sign as negative. And finally, there can be heat generation, and summation of all these heat transfer involved will be 0. Now here, this Q dot G will be 0 because I am considering rate of heat generation as 0. So after simplifying this equation, it will become Qx is equal to Qx plus dx plus Q convected. Now please put the expressions for Qx plus dx and Q convected. Already we have equations for Qx plus dx and Q convected. Okay, so this is equation for Qx. Qx plus dx, and this is expression for Q convected. Left hand side will remain same when I take into consideration the derivative of the entire term. It will become, right hand side will become equal to minus KAC dtx by dx minus KAC d square dx over dx square into dx plus h into p into dx ts minus t infinity. Now these two terms will cancel out each other. So what will remain? Left hand side will be 0. On the right hand side, minus KAC d square dx over dx square into dx plus h into p into dx ts minus t infinity. After simplifying or rearranging, it will become KAC d square dx over dx square into dx minus h into p dx ts minus t infinity is equal to 0. In both these terms, dx is common, so it will get cancelled out. So what will remain? This will be remaining. D square dx over dx square minus hp over kac ts minus infinity is equal to 0. Let's say this is equation number 4. Or d square dx over dx square minus m square ts minus infinity is equal to 0. This will be the equation 5. In above equation number 5, m square it is nothing but hp over kac, or m is equal to square root of hp over kac. M is called as a constant, Field constant, and its unit is per meter. Now equation 5 can further be simplified in terms of one dependent variable, and this dependent variable is called as excess temperature. How this excess temperature is defined? If I want to define the excess temperature for variation of temperature in the x direction, it will be theta x, and it can be given as Tx minus T infinity, where Tx is the temperature of fin at any distance x T infinity is the surrounding temperature. Similarly, I want to show the excess temperature for surface temperature. Ts minus T infinity can be represented as theta x. Okay. So here please pay attention. Excess temperature is always calculated with reference to the surrounding temperature. Okay. For fin temperature, X minus infinity theta x. For base surface, X minus infinity will be theta x. So d theta x over dx can be equivalent to dtx over dx, and d square theta x over dx square can be written as this. Okay. So let us now simplify the equation 5 in terms of excess temperature. So it will become d square theta x over dx square minus m square theta s is equal to 0. This is equation number 6. Now equation 4, 5 and 6 are called as governing differential equation for one-dimensional steady-state heat conduction through a fin or rod. Okay. Equation number 4, equation number 5 and equation number 6. Now if you closely observe equation number 4, 5 and 6, it is linear homogeneous differential equation of second order. Please mind well this term. Linear homogeneous second order differential equation. And what is the purpose of this equation 4, 5 and 6? If I could solve this equation 4, 5 or 6, I will get the equation for Tx, and with the help of that equation I can find out the variation of temperature of the fin at any distance x. Okay. So solution of equation 4, 5 or 6 will be, can be given as like this. Theta x is equal to C1 e to power mx plus C2 e to power minus mx. Sorry. The solution of the equation 4, 5, 6 will have two parts, complementary function plus particular integral. And when you solve this equation, you will get solution in this form. Okay, let's say this is equation number 7. In this equation, C1 and C2 are constants. And how can I get the values of that constants? For that, I will be requiring boundary conditions. So यहाँ पे देखिए, here as you can see theta x is nothing but Tx minus T infinity. So here, if you know the value of C1 and C2 constant, you just put the value of x. X is the distance from the base surface along the length of the fin. And just by putting the value of x, you can calculate the temperature Tx at any distance Tx. So this is the utility of this equation number 4, 5 and 6. That is why it is called as governing differential equation for heat transfer or heat conduction through fluids.